Before we dive into the chemistry of rubber, why not get warmed up? Go ahead and scan this QR code or pop over to mcqspm.com. You can practice actual past year questions on this very topic there. You know, the best way to really get this stuff to stick is by doing, so let's jump right in. Hey there, future chemists. Welcome. Today, we're diving into a topic that is literally all around you, from the tires on a car to the gloves in a lab: natural rubber. We're going to uncover the incredible chemical story of how we turn a sticky, gooey liquid from a tree into one of the most important materials on the planet. This is a huge topic for your SPM exam, so let's make sure you absolutely nail it. So here's our game plan for today. We'll start with the secret life of latex. Then we'll solve what I call the coagulation conundrum. After that, it's the vulcanization revolution. And finally, we'll put our knowledge to the test with some real exam questions, leaving you with the ultimate study guide. Ready? Let's go. Okay, let's get right into it. To really understand rubber, we need to zoom in, way in, down to the molecular level. So what exactly is that white, milky stuff that drips from a rubber tree? It all boils down to these two key ideas. Natural rubber is a polymer. Now, just think of a polymer as a super long chain, like a necklace. And each individual bead on that necklace, that's what we call a monomer. For natural rubber, that long chain is called polyisoprene because, you guessed it, the monomer, that single repeating bead, is a molecule called isoprene. And you're going to want to write this down because this is absolutely crucial for your exam. The official IUPAC name for isoprene is 2-methyl-but-1,3-diene. Examiners love asking for this exact name, so just memorizing this could be an easy point for you. But here's the catch. In its natural state, this unvulcanized rubber, well, it's not all that useful. It's soft, it gets really sticky when it's hot, and honestly, it's not very strong. The best way to think about it is like a bowl of cooked spaghetti. The long polymer chains can just slide right past each other super easily, right? That's exactly what's happening here, and that's what makes the material so weak. Okay, so that's the solid rubber. But what about the liquid latex before it even gets to that point? Well, rubber tappers face this big chemical problem every single day. How do you stop the liquid latex from turning into a solid mess before you can even get it to the factory? Let's solve this little conundrum. You see, latex is what chemists call a colloid. It's basically a bunch of tiny rubber particles just floating around in water. Now, here's the cool part. Each one of those little particles is wrapped in a protein membrane that has a negative charge. And what do two negative charges do? They repel each other. It's this repulsion that keeps all the particles pushed apart and keeps the latex nice and liquid. So if we want it to turn solid or coagulate, we've got to get rid of that repulsion. How do we do it? Simple. We add an acid. The acid releases positively charged hydrogen ions, or H+. These positive ions rush in and neutralize all those negative charges on the protein membranes. Suddenly, there's nothing keeping the particles apart anymore. They start crashing into each other, the membranes break, and the long polymer chains get all tangled up. And boom, your liquid latex coagulates into solid rubber. Now pay close attention, because this slide highlights a classic exam trap, mixing up coagulants and anticoagulants. It's actually really straightforward. If you want to make latex solid, you need to add something with a positive charge to cancel out the negative. So you add an acid, like formic acid. To keep it liquid, you do the exact opposite. You add an alkali, like an ammonia solution. Its OH- ions make sure any stray acids get neutralized, keeping the particles repelling each other. Just remember, acid for solid, alkali for liquid. Got it? Okay, so we figured out how to control whether latex is liquid or solid, but we still have that weak, sticky, spaghetti-like rubber. How on earth did we turn that into the super material we use today? This, my friends, is where the story gets really interesting. The answer came from a guy named Charles Goodyear back in 1839, and believe it or not, it was a complete accident. After years of trying to improve rubber, he accidentally dropped a mixture of rubber and sulfur onto a hot stove. But instead of melting into a gooey mess, it hardened into this tough, flexible material. He had stumbled upon the secret to making rubber amazing, and he called the process vulcanization. So what was actually happening chemically on that hot stove? Well, vulcanization is just a fancy word for heating natural rubber with sulfur. What happens is the sulfur atoms wedge themselves between those long polyisoprene chains and form strong bonds, or what we call crosslinks. And this image right here shows the difference perfectly.
On the left, that's our spaghetti, the unvulcanized polymer chains, all loosey-goosey, sliding past each other. But on the right, after vulcanization, you can see how those sulfur crosslinks have tied all the spaghetti strands together. It's not spaghetti anymore. It's a fishnet. You can stretch the net, sure, but those knots, the sulfur crosslinks, are going to pull it right back to its original shape and stop the strands from falling apart.
These sulfur crosslinks are a total game changer. First, they literally stop the polymer chains from sliding, which makes the rubber way stronger and harder. Second, they act like anchors, so when you stretch the rubber, they pull it back into shape, making it much more elastic. And finally, they protect the whole structure, making the rubber much more resistant to heat and even to damage from oxygen in the air. All right, section 4. We've got the science down. Now let's see how this all works in the real world, and more importantly, how you might see it pop up on your SPM exam. Here's a perfect example from a past year paper. It's practical, and it gets right to the heart of what we've been talking about. So think about a car tire for a second. What does it need to do? It's got to be tough, right? It needs to handle heat, friction, bumps in the road. So which properties are going to be the most important here? Let's think this through. Tires have to be super strong and durable to support a car and not wear out too fast, so strength is key. They also have to be flexible to absorb shocks and bounce back to give a smooth ride. That sounds a lot like elasticity, and vulcanization gives us both of these. So the answer is definitely going to be about its high strength and its excellent elasticity. See? Simple, once you know the chemistry. Okay, let's wrap this all up in a neat little package for our final section. This is your ultimate study guide. If you only remember one thing from today for your exam, make it this next slide. I'm serious. Go ahead and take a screenshot of this. This is your perfect revision note. Before vulcanization, rubber is soft, not very elastic, melts easily, and gets damaged by air. After vulcanization, every single one of those properties gets a massive upgrade. It becomes hard, way more elastic, super resistant to heat and oxidation, and incredibly strong. This table tells the whole story. And I'll leave you with a little something to think about. We've seen the magic that sulfur can do when it creates those crosslinks. But chemistry is all about asking, what if? So what other elements or molecules do you think could be used to create crosslinks? And what kind of new, amazing, futuristic properties could we give to polymers by doing that? That's the kind of question that drives science forward. Keep that curiosity burning, and you'll go far.